So, second main speaker is Saul Schleimer from Warwick, who will talk about minimal Ciphered Surfaces. Catchy title, that was one.
Thank you for the introduction, and also thank you for inviting me to speak, for inviting us to speak. I'm going to speak on minimal surfaces and ciphered surfaces. So let me just begin with surfaces as sort of a warm-up. So here's some, they're not even 2D printed, they're drawings with chalk. Here's sort of a collection of surfaces. Let me just say what a surface is. So a line is one-dimensional, sort of like on a train. You can just go forwards and you can go back. And of course, back is the negation of forward. So that's really one degree of freedom, or one real number, which tells you where you are on the train. You're in this coach, or in this coach, or in this coach, and, well, in this seat, or in this seat, but that's sort of more decimal places of the number. Right? So that's a one-dimensional object, a train, or a straight line. So a surface is a two-dimensional object. I think I have some poetic language here saying the acrobat on the high wire, so has one degree of freedom. The acrobat can only go forwards or back. So the acrobat in the train carriage can also only go forwards or back. Maybe less poetic, but more. The dancer on the stage, so if you're walking around on a large piazza, if you're walking around in a large quadrangle, then you have 2 degrees of freedom, right? Because where you are on the stage, say, that's a 2-dimensional thing, that requires 2 numbers to tell you where you are. You have 2 degrees of freedom. And then, of course, if you can fly, you would have a 3rd degree of freedom, and you'd be in something 3-dimensional. Okay, so now I have all my surfaces. So let me just go through and give them their names. There's the disk, which is sort of maybe the first surface that you think of. It's flat. It's just a piece of the plane. Looks like a pancake. The shading is there just to indicate that it has this inside. It's not just a circle. It actually has some 2-dimensional content. And what you can do is you can take 2 copies of the disk, and you can take their boundaries, which is the circle, and you can glue them together, and that will give you a 2-sphere. It's a 2-sphere. It lives, my hands live in 3-dimensional space, but the 2-sphere is a 2-dimensional thing, because you only have 2 degrees of freedom when you're stuck on a 2-sphere. Right? Just like when you're stuck on a stage, it only requires 2 numbers to specify where you are. On the stage, or on the plane, it's my x-coordinate and my y-coordinate. On the sphere, it would be my longitude and my latitude. Okay? So that's a 2-dimensional object. And you get the sphere from the disk by doing this process of doubling, this process of taking 2 copies and gluing them along their boundary. So that's a very topological operation. So what's next in my rogues gallery of surfaces? The annulus and the torus. So there's the annulus. It's just a disk where you've cut out a smaller disk. Okay? We have something 2-dimensional, and we cut out a smaller 2-dimensional thing, and we get the annulus. It's also called a ring. And if I do this doubling procedure, where I take 2 annuli and I glue them along their boundaries, so there's 2 boundaries to glue along now, then I get what's called the 2 torus. And the 2 torus is very familiar. It is the boundary of a donut, or the boundary of a bagel. Next in my rogues gallery is something which is non-orientable. You have to make it in a more interesting way. It needs a little bit of a twist. This is the Mbius Band, again drawn in chalk. And the Mbius Band, it's very similar to the annulus. You can make an annulus by taking a long strip of paper and gluing the short ends together. And you can make a Mbius Band by taking the same long strip of paper and giving a half twist before you glue the ends together. So, and if you double the Mbius Band, then you'll get what's called a Klein bottle. And the Klein bottle, finally, the drawing is quite complicated, and there's this bizarre little business here, which is where it looks like it's self-intersecting itself. So the Klein bottle doesn't self-intersect in this way. This is just an artifact of the way that we have to draw in 3 space, because it's impossible to have a non-orientable surface, closed non-orientable surface in 3 space without it crashing through itself in some complicated way. So this is a theorem in topology, but suffice to say, if you take a Mbius Band and double it, you get the Klein bottle. So let me just throw a bone to higher genus. So here's a surface of genus 2 with 1 boundary component. So I would say in one way of saying it is that this has one hole, it's got one boundary component, and it's got two handles, right? There's two places where you can kind of grab it and hold it. Like a piece of luggage, it's got, well, for example, one handle on the top and one handle on the side, so that would be genus 2. And sometimes there's a sneaky handle on the bottom, and then it would have genus 3. Okay? So just notice that if you take this genus 2 surface with one boundary component and you double it, then you get a surface without boundary. This edge, the place where you could go and have to stop, that's gone away. But now the genus is doubled, right? Which really makes sense, right? If you double a surface, then you deserve for its genus to double. The disk had genus 0. I doubled it, and I got the sphere, which also had genus 0. The annulus, don't ask me about the annulus. OK, good. So that's the topology of surfaces. Let me just say a word, a very quick word, or really just draw a picture about the geometry of surfaces. So here we are. And here again are my cartoons. The cap, or the cup, I guess a bowl shape really. Here's the disk again. And here's a saddle. And then there's an equation. I'm reliably informed that every equation that you put in your talk puts half of the audience to sleep, or some words to that effect. So please don't fall asleep. This is just to remind me to talk about curvature. So if you have a topological surface, it doesn't have any particular preferred position, right? It's a surface, and in rubber sheet topology, you're allowed to take the surface and you're allowed to move it around as long as you don't tear it or cut it with a pair of scissors. You're allowed to deform it. This famous saying is that to a topologist, a donut and a coffee cup are the same thing because they both have one handle. Okay? So, but if you have an actual surface actually sitting in space, then it has a particular shape. And it has angles, and it has lengths, and it encloses some volume if it's closed. Okay? It has all these geometrical properties. It has things that you can measure, which are more analytic than just the number of holes. It's things that you can measure, not things that you count. Okay? That's the difference between topology and geometry. In geometry, you measure things. Geometry, earth measurement, right? And topology, study of shapes, roughly, if you want to do a bad translation. So, and then I have my formula, which is supposed to say something about curvature. So here we go. At this south pole of the bowl right here, there are two directions we can go in. We can either go in the plane of the board, or in the plane of the screen, or into the screen, parallel to the screen or into the screen. And we get these two directions we can travel, and they both curve up, let's say. Okay? And if we walk through the origin in the disk right here, then there's again two directions we can go, and they both stay flat. And finally, here's the saddle. There's two directions we can go. We can go up to the saddle and then down, or we can come down from the mountaintop, get to the saddle, decide that we don't want to go down to the common world, and go back up to the mountaintop. Well, a different mountaintop. Well, perhaps the same mountaintop if the topology works that way, but in any case, a mountaintop. So what's going on is that here, the two paths curve away in the same direction, and here they curve away but in opposite directions. So we would say that this has positive curvature, this has zero curvature, and this has negative curvature. Okay? When we see a saddle shape, that is okay, so the positive and negative, that's not like saying positive is good and negative is bad. We don't really have an opinion. Certain mathematicians might prefer to work with positive curvature things. Certain mathematicians might prefer to work with negative curvature things. I'm a three-dimensional topologist, so I've been trained from an early age to think that negative curvature is more interesting. But the geometers tell me that that's not really true, and there's super cool things that you can say about positively curved manifolds as well. So we have so positive and negative are not epithets. They're simply the labels that we've given. So what I want to say with this little equation right here is to say that what negative curvature means actually depends on what space you're in. So a surface by itself, just topological, it doesn't have a shape. We have to give it a shape. One way of giving it a shape is by putting it into a space. And the classical thing to do is to put it in 3 space and then measure its principal curvatures and take their product. And this is this little symbol right here. But as Henry talked about, and I know that you didn't fall asleep during his talk and you understood everything he said, so I'm allowed to talk about the 3-sphere now, is Henry said that you can put lots of interesting objects in the 3-sphere. And that's one of the things that we want to do. A lot of the topological objects, they have their most interesting positions in the 3-sphere. And when you have a more interesting manifold than the ambient space, the ambient curvature, affects the shape of the surface. So let me just leave it at that. This equation is supposed to remind me to say that when a surface is living in a cool three-dimensional space, which is not just flat space, not Euclidean space, then the shape of the ambient space has something to say about the curvature of the surface. Okay, so that's enough about surfaces. Minimal surfaces. So what is a minimal surface? Minimality means area. When we're talking about a minimal surface, we're trying to reduce its area. So that's no problem. Just take your surface and just put it in a bag and crush it. Okay, now it's area 0. No problem. We solved the problem. Well, okay, so that is saying that we need a constraint. We can't just crush things. We need to have a side condition which prevents the problem from being degenerate. And there's two ways to proceed. A soap film here on a wireframe, or a soap film with no wireframe, right? So this is a little disk, and this is a sphere. I hope that you remember, right? Disk, sphere, those are my first guys in my rogues gallery. Good. So what's a soap film? A soap film on a wireframe, there's a condition on the boundary. The soap film must have that boundary. And amongst all surfaces with that boundary, the soap film is the one with the least area, right? So again, we're minimizing area subject to a constraint. And in the first example, in Plateau's problem, the constraint is, what's the boundary? In the second picture, we just have a bubble. There's no boundary, right? When I double, I got rid of the boundary, right? So now what's going on, the constraint is that the bubble must contain a certain volume of air, right? The air is not allowed to move from one side of the bubble to the other, right? I guess it could osmose out very slowly, but the bubble will pop before then. So given that it contains that volume, what's the least area surface that contains that volume? And the solution to that problem, the isoparametric problem, is the sphere. Okay? In these pictures were taken in Kenilworth, which is near Warwick. So space is flat there. So the ambient metric is flat, and so we get the solutions that we're used to, namely these two. Okay, so minimal surfaces do the expected thing. Great, so those are the first two surfaces in my rogues gallery. Here's the, oh, right. I had a little note to remind myself that we are going to pay more attention to Plateau's problem because we think that surfaces with boundary are really cool. So, but the isoparametric problem is also super cool, right? So I will say a minimal surface is one that solves Plateau's problem. A minimal surface is a surface that solves Plateau's problem locally. So for any little patch of the surface, it has to be the minimal surface with that boundary. So let me give an example to make that clear. So here's the next surface, which is the annulus. And this is a minimal annulus. I have a wireframe. I'm solving Plateau's problem, right? I have to have that boundary. And subject to having that boundary, this surface is the one with the least area. And it's called the catenoid. And let me just remark that these are really hard to photograph. So you spend a lot of time trying to, well, we'll spend a lot of time with soap solution and try and not get it on the camera and trying to get the sun just right and trying to not get your fingers in the picture. And then it pops. And so you have to start over. OK, so that said, here's the catenoid. And this is an annulus in R3. Remember, I said that Kenilworth is locally flat. So this is the ambient curvature is 0. So if you want to have, there's another annulus. There's another way to put the annulus in 3 space, and that's as the Hoff band. Okay, so here again we're solving Plateau's problem. We have 2 loops, right? But now instead of the loops being disjoint from each other, and we have an annulus that spans between them, the 2 loops link each other just once. And the annulus again spans between them. And just so you can see, it's very flat near the wireframe, and it's very flat near the wireframe. But where it's transitioning between one wireframe and the other, there's this sort of, it's quite negatively curved there and there. And you can see that there's a hole, as there has to be for the annulus. Okay? So again, this is what you get solving Plateau's problem in Kenilworth, which is flat. All right? So if we go to S3, then we get this instead. Okay? And so maybe something to notice is that it's not nearly as flat near the wireframe. And here it looks like it's straying quite far away from the wireframe right there. appearances can be deceptive. This is actually not in S3. This is in the stereographic projection from S3 to R3. So geometry is being distorted. And let me just say, the geometry looks sort of slightly negatively curved here. And it looks kind of flat right there. You can see there's this straight line. And anytime you have a straight line in a surface, then the curvature has to be 0. And that's actually an artifact. This guy is negatively curved everywhere. Okay? The stereographic projection is most faithful near the origin, which is around there, I guess. So there's no surface there. But this is pretty close to the origin, and you can see that it's negatively curved, even close to the wireframe. Okay? And so what's going on is the equation that I put on the board, it looks, well, what am I trying to say? I'm trying to say that the annulus is intrinsically totally flat, but it looks negatively curved because it's got to be more negatively curved than the 3-sphere, which is actually positively curved. Whew, that's a mouthful. Let me just show you what happens if you rotate the Hoff band around its boundary. There's this Hoff band right here, and it's got this ring, right? This red boundary component. I'm just going to rotate it around by pi. Okay? Because remember, S3, it's very round, so it's got some symmetries which are unusual. You can't do that in R3. But in S3, we can just rotate it by 180 degrees, and we get this other guy, right? So I have the one I started with, and I rotate it by angle pi, and I get the one on the outside, or the other side, I guess. So this one looks much bigger, but remember, there's a point at infinity for S3. So the whole outside here, we're just getting close to the point at infinity. And then we can take the two of them together, and this is called the Clifford Taurus. Okay? So this is my procedure of doubling. I have an annulus. I take 2 copies of the annulus, and I glue them together along their boundary, and I get the Clifford Taurus. And I have one here. So let me just show you what it looks like on the document camera. Oops, sorry about that. Good. So maybe one thing to notice is that the Clifford Taurus, it's filled up by these lines, which are all great circles in the sphere, and these lines are at right angles to each other. And I claim that this is close to be, and it's very symmetric. If you turn it over, it's hard to tell that you've done anything. And it has these cool holes that are running through it. Why don't I just pass this around so that you can take a closer look? Thank you. Oh, actually, Henry, I noticed that these guys were being skipped. Try and alternate. Right. Let me just make a quick observation. You see all these squares? I claim that in S3, that's actually a square with this side length equal to that side length. And because S3 is so symmetric, you can see that you can prove that this square is the same size as this square in S3. Not here. The stereographic projection distorts distances, remember. And the further away you are from the origin, the bigger it blows things up. As you remember from Henry's projecting things on the wall, there was small stuff in the center, and there was big things near the outside. And they were the same size on the 2-sphere, but things, so in other words, stereographic projection is stretching things as they get to the North Pole. So you can see that in this picture as well. You can see it in all the pictures. Here's the origin. Things are being faithfully represented here. Here things are being stretched by, I don't know, probably a factor of 2 or so. Oh, that's not correct. Probably a factor of a little bit more than 2. And here things are being quite badly stretched because we're getting closer to the North Pole. Right? So I claim that this stretching, that's just an artifact of stereographic projection. All of these disks are identical. Yeah? And since they're 4 around a vertex, that means this thing's locally flat. The intrinsic curvature of this surface wants to be just like the stage. It wants to be flat. Okay? So then, I hear you ask, why on earth does it look so negatively curved? Right? You can see that there's a total saddle shape right there at the origin, right? And there's quite nice negative curvature all over the shop. Right? So this thing, it's intrinsically flat, but obviously it's negatively curved. The reason why is because it's a flat thing inside of a round space. S3 is very round. It's got positive curvature, and this thing has 0 curvature. So if you have less curvature than your ambient, you look negatively curved. That's the That's sort of the catchphrase. That's what my equation was trying to say mathematically. But morally, if you're minimal and if you're minimal, then you look negatively curved with respect to your ambient. That's one way to say it. Good. Okay. Since this guy is not just minimal, it's also got zero curvature. 0 is less than 1, so it's negatively curved with respect to its ambient space. Okay, so then we can do the same thing for the Mbius band. And let me pass one of those around as well. I think I start this side this time. So this Mbius band, it's the maximally symmetric Mbius band in S3. You can see this circle. That's a circle of symmetry. This thing actually has a rotation symmetry around that. It doesn't look like it does because it's got a big lobe here and a little lobe there. But remember, in S3, sizes are different. And you can actually take this guy and rotate this part into that part and then keep rotating around. And again, it's tiled by squares. I claim that all of these squares, oh, that's not true. It's not true that all these squares are identical. Oop. It's true that all of these squares right next to the circle are identical to each other. And it's true that all of these squares, which are one step away from the circle, are identical. But they're not necessarily all identical to each other. And I think that they're not. Never mind. Moving forward. And here I've given a parameterization, just to show you that you can parameterize it analytically. So if I take this thing and I double it, here's one Mbius band. I took it and I rotated it by 90 degrees. And if I double across the round boundary, then I get the Klein bottle. And again, you see that there's a self-intersection. Here's the Klein bottle, the maximally symmetric Klein bottle living in S3. And a non-orientable surface, it has to self-intersect in a three-dimensional. That's not true. A non-orientable surface in the three-sphere has to self-intersect. So we get this line of intersection here. And let me pass that around as well. So here's the maximally symmetric Klein bottle. And if you stare along it, you can see that there's this order 4 symmetry point, which is the line of intersection. OK, so all of these minimal surfaces are very special cases of a construction of Lawson, written down in a paper in 1970. So let me show you one more, or two more, rather, examples of the Lawson surfaces. Here's a surface of genus 6, and here is a surface of genus 4. Both minimal surfaces in the three-sphere. And you see the usual business. This region here is isometric to that region here. Isometric is a fancy word for meaning the same as. And you can see that we're blowing up as we go towards the North Pole. And the same kind of property is happening here. This point, the point down there, that point, and the point at infinity, those are all the same. But they seem to have different shapes once we do the stereographic projection. This surface is rendered by Nicholas Schmidt, and we drew this one using Surface Evolver, a program of Ken Bracke. Good. So those are the minimal surfaces. I'd now like to talk about the ciphered surfaces. So ciphered surfaces are surfaces that span a knot. A knot is a loop in space. Again, it's just some topological thing, so we don't know what position it has. Let me get one here. So here's my knot. It's quite complicated, but if you follow it with your finger, you can see that it's a single loop in space. And just as it's defined, just as it's given to us, it's just a loop in space. So you can grab it with your finger and move it around. As long as you don't cross it, as long as it doesn't cross itself, that's the same knot, basically. So we don't get a position. We have to find a best position and use that. So I claim that this is very close to being the best position. Here, I have a few more knots, so why don't I hand those out. I have 2 copies of this. So there's no canonical position. Let's instead find the canonical position. Here's the definition. A knot, a loop in space, is a torus knot if we can put it on the Clifford torus. Okay? If we can put it on the boundary of a donut. So where is the donut? I hear you cry. There's the donut. Okay? And you can see the knot. It's swooshing around, and it goes through the hole, and it comes back out, and goes through the hole again, and comes back out, and goes through the hole, it comes out back out again, and then we've gotten back to where we started. Okay? And so what we did is we went through the hole 4 times, and if you counted how long it took, I went around once, twice, 3 times. Right? So a torus secretly has a pair of holes, or a pair of handles. I mean, it just has one handle, but there are 2 different ways to look at the handle. Does someone have the Clifford Taurus? Could you sort of hold it up? Just hold it up. Right. So if you look at it, and when I flipped it over on the document camera, right, it was symmetric. I flipped it over, and you couldn't really tell the difference. So whether the handle's the top one or the bottom one, you can't really tell. So thank you very much. So in other words, when you're going through the hole, you get to ask which hole you mean, right? And that gives you 2 numbers, not just 1, right? This goes through the obvious hole 4 times, and the secret hidden hole, it goes through it 3 times. Okay? So those 2 numbers, they specify the torus knot. I think I have another drawing of exactly that thing. Right? What I did is I took the torus and I cut it along this curve right there, and I cut it along that curve right there. And when you cut it, because it's really flat, you get a flat piece of paper. You get a square. Okay? And then the red guy, it becomes these curves. I had to cut the torus open, and when I cut the torus open, I unavoidably cut the torus knot too. And in fact, I cut it in 1, 2, 3 points. That point, 1, 2, 3, 4 points, and 1, 2, 3 points. Okay, and that's the 4 and the 3 again. Right, so we've got the torus knot. We've got it on the torus. The torus is an S3, so everything's going hunky-dory. Now we just need to find the spanning surface. This is my choice of wireframe, this red thing. So now I need to find the soap film, which spans it. Okay, so we need an idea which is due to Herbert Seifert, which is the idea of the Ciphered Surface. This is an illustration from his paper in 1934 where he introduces it. And he does draw torus knots in that paper, but he doesn't draw any Ciphered surfaces for torus knots. Very sad. Otherwise, I would have used that instead. And this is 3 pictures of, This is 3 pictures of the same Ciphered surface. 1, 2, 3. And what's going on is the Ciphered surface is a disk with 2 bands attached to it, like that. So you take a disk, that was our very first surface, and you attach 2 strips to it in this sort of knotted way. And that gives you a 2-dimensional thing with a boundary, with a 1-dimensional boundary, and that's our Ciphered surface. The boundary is the knot, and the surface is the thing that spans it. And then the sequence of pictures is showing you how to deform a Ciphered surface to put it into this particularly nice position. This is not always possible for all Ciphered surfaces, but this is one that he was particularly interested in. Good. By the way, 3-dimensional topologists are just crazy about Ciphered surfaces because, well, first of all, they're 2-dimensional, which is a lot easier than 3-dimensional things. And second of all, they kind of serve as a bridge. The knot's 1-dimensional, but it's sitting in an ambient space of 3 dimensions. So the Ciphered surface is something which is sort of in between, and it can help you get a handle on the topology of the knot, right? It sort of translates between the 1-dimensionality and the 3-dimensionality, because it's a 2-dimensional thing, maybe. Okay, good. So that's Ciphered surfaces. So now I'm going to find Ciphered surfaces for torus knots. So here's another equation. So I guess I've only got a fourth of my audience left. Three quarters are asleep. So the equation is w to the p plus z to the q. So it's kind of like x squared plus y squared. It's kind of like the equation for a circle. Okay? Except the p and the q, that's the 4 and the 3 that I was talking about before. Right? We take this equation in C2, right? And we cut out this complex curve, and we intersect it with S3, and we get the torus knot. And if we use this, if we look at all the points which the argument is theta, we get a Ciphered surface. What does that mean? Who knows? Instead, let me show you some picture of what it looks like. So here is an example of my Ciphered surface. Here the invariants are 5. You can see 5-fold symmetry. And the invariants are 3. You can see 3 stacks, 3 pancakes. So back to the 5-fold view. All these little decorations on it, those are windows that we cut in the surface for your viewing pleasure. You should ignore those. Those interrupt the two-dimensionality. Just fill in all the windows. And then you can see that it has this boundary. That's the 5-3 torus knot. And this surface in white is the thing spanning the torus knot. Let me hand out a couple of these for you guys to look at. I'll keep one for myself. Good. So that's the ciphered surface. How did we make it? That's sort of the question. And how can we get away with this claim that this is the best position, right? Because that's always the goal. We want to find the best position of the object so that we can draw it, right? If it's just topological, it wiggles around in space. We don't have a particular position that we prefer any one position over the other, right? So to draw something, we're making a choice. We'd like to make the best possible choice. How do we make that choice? Well, we use the Milnor fiber, which is the thing that solves this equation. That's not good enough for us. This is a implicit definition of the Milnor fiber. This says it's all the z's and w's that solve this equation. That's not a way to draw it. To draw it, we need a parameterization. Here's how we find the parameterization. Start with a Euclidean triangle with angle pi on 4 and pi on 3. Okay? That's the 4 and the 3 that I started with. And why did we choose the Euclidean triangle? It's because it's super duper easy to draw pictures in the Euclidean triangle. So we just draw these triangles. Those are going to be the windows. And we're going to push them all the way forward until we get the actual surface. So what's this pushing forward procedure? What pictures do we draw along the way towards our final construction? Take this triangle and smooth it out to a copy of the Poincare disk. Here, the angle is pi on 3. Here, the angle is pi. Here, the angle is pi on 4. Here, the angle is pi. So we invert the incomplete beta function, which is fancy words for saying we do some complex analysis. Actually, taking an inverse makes things difficult. Going from the disk to the triangle is really easy for some reason. I mean, it's not easy, but it's well known, and it's just a function that you can use in Mathematica. Going from the triangle to the disk is kind of hard, and we needed to do a bunch of mathematics to even do that. OK, fine. So we've gotten from the triangle to the disk. Now we're going to go from the disk to the hyperbolic plane. So the hyperbolic plane is this thing of negative curvature. It's got lots of symmetries, way more than the sphere or the regular plane. And you can see that we've gotten lots and lots of copies of our original tile. But let me just talk about the original tile. Here's the Poincare disk. We map it to the red region. And these points, the special points with angle pi, they now have angle back to the original angle. This is pi on 4, and that's pi on 3. So to do this, we use a variant of the Schwarz-Christoffel map, more complex analysis. Finally, this is all complex analysis that can be done and is written down in various books. So here's the last step, which is only written down in papers. And even then, there's work to be done. We have to take the tiling of the hyperbolic plane and turn it into a tiling of the ciphered surface in S3. So this is a universal covering map. And that's a bit of topology. And to find this tiling, to find the map which takes a point in the hyperbolic plane and sends it to a point in S3, we need to use what are called fractional automorphic forms, which is something from number theory. And we also have to use Q-series in order to actually explicitly give the fractional automorphic forms. So, and much of this work is originally done in a paper of Milnor and explicated in a paper of Tsanov, and finding the Q-series is some sort of well-known number theory, but you still have to do it. So at the end of the day, you get your optimal surface. This is a copy of the Milnor fiber, and it is parameterized via this sequence of complex analytic maps, where the last step is really the most significant, because this map you actually have to do for yourself. You can't. these choices, you can parameterize the hyperbolic plane any way you like, as long as you respect the tiling by the big red triangle. But finally mapping from the red triangle into the surface is something that is something new. Fine. Once you've done all this work, then you can produce the surfaces and more. Let me say it again. Here's the Ciphered surface. But remember this business I did with the Clifford Taurus? I said, oh, look, as long as you're in S3, you can rotate by pi. Okay? So we can do the same thing here. I can either parameterize the surface, or I can pick a point on the surface and I can push it around the 3 sphere. Okay? And this business of pushing it around, that will produce these tubes. Right? You can either move sideways on the surface, and then you always stay on the surface. That's 2-dimensional. Or you can leap off the surface and follow a flow line, a line of the elliptic flow, and that will produce these tubes. You could push the whole surface around, but then you'd fill up all of space, and you wouldn't be able to see anything. Let me just sort of show you the process of turning the tile into the whole Ciphered surface. And this is now, there's no mathematics. This is more like a Disney cartoon. This is animation. So here's our torus knot. Again, the trustworthy 4-3 torus knot. And there's the torus. Let's turn it sideways so we can kind of see into the, what I want here is a better view of the origin, where the geometry is most faithfully reproduced by stereographic projection. Out here, near the North Pole, remember, things are being wildly distorted. But near the origin, things are pretty honest. And what you see in R3 is pretty much the same as what you see in S3. Good. So let's get rid of the torus. We don't need that. Let's zoom in, because we want to get a little closer to the origin and see what's really going on, where the picture is geometrically honest. I mean, it's always honest combinatorially, and it's always conformally correct. So it's always honest in some sense. But it's geometrically quasi-honest near the origin. OK, good. So let's make the knot a little thinner so it doesn't get in the way. And let's draw our first tile. And this is actually 2 tiles. There's this guy right here, this blue triangle, and it's going along the knot. And this other blue triangle, that's its double. Right? Anytime I want, I can take the surface and I can double it across its boundary. And so that's what I've done here. I'm not just doing the Ciphered surface at angle 0. This here is the Ciphered surface at angle 0. I'm also doing the Ciphered surface at angle pi. OK? And one way to think of that is I'm taking this triangle and I'm rotating it by pi around the knot to get to the other triangle. So those are my two triangles, and they together form this kind of Pringle shape. And I have 4 of these Pringles, because one of my magic numbers was 4. OK? And then let's make that a little smaller. Zoom away a little bit. And then this lens, I have a whole collection of those, and they alternate being on and off, because at this point right here, I need to have a kind of a monkey saddle. So where's my next lens? There's my next lens. And there's the next one. And there's the next one. There's the second to last one. And there's the last lens. Now I've built the doubled Ciphered surface. OK? And the knot divides the Ciphered surface, this double, into 2 pieces, the original Ciphered surface and the rotation by pi. And let me just show you the original. There it is. And let me show you the rotation by pi. And there they are together. OK? So this looks an awful lot like Lawson's surface, doesn't it? The doubled Ciphered surface, there it is. It's got this monkey saddle here. It's got these lobes. It's got this stuff going off to infinity. There's the Lawson surface I showed you. It's got these monkey saddle here. It's got this lobe going off to infinity. They look the same. They really do. I thought they were the same. Oh, I guess that means that they're not. OK, they could be the same. That would be super cool. Oh, and look, the knot, actually, this is true. This is not a lie. The red knot lies on both of them in exactly the same way and cuts them into 2 pieces in the same way. So they're not the same. OK? Here's the computer proof that they're not the same. They look totally the same. If you superimpose them, the red guy just looks painted on. OK? It looks like makeup, basically. Yeah? But if you sort of shift sideways, so where did I go? I want to go right here. Like along here, they are the same. They agree. And on the knot, they are the same. They agree. OK? So what I need to do is I need to go to the center of here, and I need to look from the side to see if there's any daylight between the 2 of them. So that's what I'm going to do. I'm going to look from the side. And you know what? They still look the same. Yeah? It still looks painted on. But if you zoom in a lot, then you see just a little bit of daylight between them. Yeah? You can actually see this red knot. That's on a different sheet of the surface running behind. Yeah? And right there, you can see that it's behind the ciphered surface, but it's in front. Or it's not in, it's behind the ciphered surface, but it's not behind yet the Lawson surface. Okay, so that's a computer proof that they're not the same surface, right? Assuming that we have enough precision and blah 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 blah. Okay, so here's a proof that's not a computer proof. It's yeah. So how many equations is that? Well, hopefully I have one person who's still awake. I'm still awake. That's good. Right. So there's some criterion due to Shang. And if you just crank through and check some vanishing thing, this is supposed to be a multiple. You print the Milnor fiber is implicitly defined by some homogeneous polynomial. Anytime you have a surface defined by a homogeneous polynomial, if it's going to be minimal, this thing had better vanish mod f. And it doesn't. You can just crank through, and you can see that this is not vanishing mod f. So they're not minimal. Too bad. Okay, they look minimal. I thought they were minimal. I was wrong. The computer proves I'm wrong, and Shang proves I'm wrong. So I'm really wrong. But hey, it's really close to being minimal. One might ask, they're so suspiciously close to being the same that maybe it deserves an explanation why they're the same. Okay, so there's one thing left. There are various questions that we had about the Milnor fiber and how it sits in S3. There's one thing which is super suspicious and we don't know the answer to, which is this is, oh my goodness, I forget which is which. One of these is the knot, and one of them is the boundary of the ciphered surface. What's that? The top one is the knot. Thank you, Henry. This one is the knot, parameterized by arc length in S3. And this one is the boundary of the ciphered surface, parameterized by complex analysis. I had all these cool pictures in the hyperbolic plane, and there was stuff going off to infinity. So this is parameterized by the Horst cyclic length around the point at infinity. And you can see this dot is right next to that change in color, and this dot is right next to that, and this dot is that. The parameterizations are the same. And we don't know why. The parameterization coming from the S3 geometry and the parameterization coming from the complex analysis, they're agreeing to as many decimal places as we can see. So they're surely the same. Oh yeah, this is a computer proof. They're the same, yeah. But we don't have the proof with all the equations. So thank you for your attention. Thank you.